Hello all of you. I'm doing a few videos on the math skills in physics. This is more useful to the students who are not doing maths for their A levels. The ones who are already doing maths, further maths, etc. will find it comparatively easier. So I'm going to start with linear graphs. All of you are already aware of what linear graphs are. So the equation for a straight line or a linear graph is y is equal to mx plus c. So you already know what y and x stands for. Y is for the coordinates along the y-axis, x is for the coordinates along the x-axis, m stands for the slope of the graph or the gradient of the graph, and c stands for the y-intercept. So if I draw a small graph next to this, so this is our c or the y-intercept, and then you have the gradient of the graph. This is our x-axis, this is our y-axis. So this much all of you are familiar with. There is nothing new in this. The gradient is delta y over delta x. Now where do we use this in physics? That is the next thing. So by now you have come across so many 6-mark questions where you have to draw a graph and the gradient of the graph, or if you manipulate the gradient of the graph, it will give you what they are asking you in the question. So how do we do that? How do you recognize that when you see an equation given to you? So we are going to take a few equations and then we are going to see how we can manipulate those equations to find out the gradient. And the first lesson we are going to take very few simple equations and then we will move on to the exponential equations. Now let's look at the first equation. V equals I times R. Potential difference is equal to current times resistance. So they have asked you a question where they're asking you to find the resistance of an unknown piece of metal wire, or they're asking you to find the value of an unknown resistor. So you will be changing the voltage across the resistor. You will measure the current that is flowing through it, and then what will we do? We will draw a graph. So if we compare this with y is equal to mx plus c, and if we plot v along the y-axis, and then what is left with us is I. So if we plot that I along the x-axis, it will then tell you that the gradient of the graph gives you the resistance. We don't have a value for c, so that tells you that the y-intercept is 0. So your graph should not have a y-intercept. Along the x-axis we have I, and along the y-axis we have v. So since it doesn't have an y-intercept, you will get a graph like this. Okay, so it can be as simple as this or a slightly different variation. I equals q over t. Current equals charge flowing divided by the time taken. So here they are asking you to draw a graph so that you can find the charge that was flowing through the conductor. So here if I take, so again if I compare it with y is equal to mx plus c, so every 1 second I am measuring how much current is flowing through the conductor. So if I take the current measured in that way along the y-axis, and if I take 1 over t along the x-axis, okay, what do I get? Then the gradient should be the charge flowing through the conductor. So again, similar to that, if I take 1 over t and if I take I, then I should get a straight line without any y intercept again this time, and the gradient is going to give me the charge. Okay, so here it was I equals Q divided by T, or this is the same as Q times 1 over T. So I want to find Q. So if I want to find Q, what I'm left is with I and 1 over T. That is why those went to those respective axes. Now a slightly different one. Resistivity rho equals RA over L. So they are again asking me to design an experiment to find the resistivity of a given material of wire. So I don't know the resistivity, so I need to find the resistance. And so what I can do here is, in order to find the resistance, I can see that it depends on the length and it depends on the area. So I can think about two things there. One, either I can change the length and measure the resistance each time, or more correctly calculate the resistance each time, or I can take the same length and change the area of the wire each time and calculate the resistance. So whichever way we want, we can do that. So what I'm going to do here is, I'm going to take different length, and for each length the voltage and current across that conductor, and then for each length I'm going to find out the resistance. So I have different lengths with me, so I will get different voltage, different current, and each time I will calculate the resistance. So if I rearrange this equation, R is equal to rho L divided by A. So I changed my L each time. So what we change generally goes to the x-axis. That is what the basic rule is. All the independent variable generally goes to the x-axis, but we don't see that in all the graphs. So say I'm taking what I changed L, so I'm taking that along the x-axis, and then the resistance that I calculated goes along the y-axis. So this is going along the y-axis. In that case, if I say y is equal to mx plus c, again R is going along the y-axis. I had L along the x-axis. So what is left? If you compare these two, you can see in place of m, I'm having rho over A, where A is the area of cross-section of the wire. So all I need to do is find the area of the wire using a micrometer screw gauge, and then that times the gradient of the graph should give me the resistance of the wire. Resistivity of the wire. So this is what I said initially, that always the gradient need not give us exactly what we want. Slightly manipulating the gradient will give us what we want. So here also we have made the given equation in the form y is equal to mx plus c, and we have, so here also we can see that there is no value for y-intercept. So the graph is going to look again like what we have seen earlier. If we take resistance along the y-axis and length along the x-axis, we should be getting a graph like this, and the gradient of the graph is resistivity over area. So how do we manipulate it? It all depends on what they are asking us to find. So if they give you this equation and ask you to find the resistivity, then this is how you have to manipulate it. Now let's take another one which you are very familiar with. You have come across this equation before when you did current electricity. So in order to find the EMF of a power supply, what did we do? We connected an external resistor across it, and then we changed the voltage and the current flowing through that external resistor, measured them both each time, and then we plotted a graph. So since we are changing, or we are measuring V and I, let's make one of them the subject of the equation. So this means V equals E minus IR. Okay, so if I make it exactly in the format of Y is equal to mx plus c, I'm just rearranging them. I've just changed the places so that it looks exactly in the same format as y is equal to mx plus c. So now we measured V, so that's going along the y-axis. We measured I also each time that we measured V, so that is going along the x-axis. So you can now see that the gradient of the graph is R, but is it just R? No, there's a negative sign, so the gradient is negative. That is very important here. And this time our y-intercept is not 0 anymore, so that is the EMF. So now if we plot a graph, we would not have a line with a positive gradient, we would have a line with a negative gradient. And this bit is our EMF. And the gradient of this graph will give you the internal resistance. Okay, so that is how, this is a slightly different equation, but you're very much familiar with this equation because you did this in your year 12. We have used this many times after that, but then I just thought to mention this because we are doing similar equations.